ME 347, Example 12. A converging nozzle is used to isentropically accelerate air from a large reservoir at high pressure and temperature of 300 Kelvin to sonic velocity. The nozzle exit area is 1 centimeter squared and the back pressure is 100 kilopascals. A. Find the stagnation pressure in the reservoir, exit temperature, mass flow rate, and volumetric flow rate of the air. B. What happens to mass flow rate if the exit area is reduced by 50% for constant stagnation conditions? C. What happens to the mass flow rate if the exit area is increased by 200%, again for constant stagnation conditions? D. Sketch the TS diagrams for parts A, B, and C. For this problem, we will assume a large reservoir at stagnation conditions. Second, we will assume steady, one-dimensional, thus uniform properties at each cross-section flow through the nozzle of an ideal gas with constant specific heats. Also, we will assume the flow is isentropic, thus frictionless and adiabatic, with negligible gravitational effects. Before we begin, let's look at a schematic diagram for this problem. First, again note that we are assuming that the air is stagnant in the large reservoir and that the specified stagnation pressure and stagnation temperature remain constant. Second, the problem stated that the flow is sonic at the exit plane, which corresponds to critical conditions. Third, because we are assuming isentropic flow, all of the properties will remain continuous. Thus, the properties in the exit plane are also equal to the properties just after the exit plane, indicated by the subscript B and referred to as the back pressure and back temperature. Later, when we have shocks in the exit plane, which are not isentropic, these properties will jump across the exit plane and not be the same. For part A, we begin our analysis by calculating the unknown stagnation pressure upstream in the tank based on the known exit pressure equal to about 1 atmosphere using the isentropic flow relations for critical conditions. The pressure needed to obtain sonic flow is 189 kilopascals, which is less than 2 atmospheres or 30 psia. Next, we calculate the exit temperature based on the known stagnation temperature in the tank at about room temperature, again using the isentropic flow relations for critical conditions. The temperature drops significantly to 250 Kelvin or minus 23 degrees Celsius. Continuing with part A, to calculate the mass flow rate, we note that because the throat is at the sonic velocities, these conditions correspond to choked flow, and we can use the corresponding equation to solve for the mass flow rate. Plugging in our parameters, we get a mass flow rate of 0.0442 kilograms per second for choked flow through a 1 centimeter squared exit. Finally, for part A, to calculate a flow rate that is easier to visualize, we will calculate the volumetric flow rate. To do this, we first need to calculate the density of the flow at the exit using the ideal gas law and the known exit pressure and temperature. Based on this, we get that the density is about 1.4 kilograms per meter cubed, which is a little higher than at STP. Finally, dividing the mass flow rate by this value and converting to liters, we get a volumetric flow rate of about 32 liters per second. That is a lot of air. For part B, we consider how changing the exit area will change the mass flow rate if we keep the stagnation conditions constant. Since the flow is choked with a constant pressure ratio across the nozzle, the critical velocity and density in the exit plane remain the same. Thus, the mass flow rate just scales with the area. For this case, both the mass flow rate and volumetric flow rate are 50% of the original values. For part C, we have the exact same constraints, so once again, the mass flow rate just scales with the area. Thus, for this case, both the mass flow rate and volumetric flow rate are double the original values. Finally, for part D, we sketch the TS diagram for parts A, B, and C. First, we note that all three cases will have the exact same diagram, where the air goes from the stagnation conditions in the tank, labeled T, to the critical conditions in the exit plane, labeled E. Second, note that the stagnation conditions will be at the maximum temperature and pressure. Third, As the flow accelerates through the nozzle, the temperature and pressure drop as the kinetic energy increases along a vertical line for our isentropic process.